understand geometrically that light from a point source can be thought of as distributed over the surface area of a sphere. Student will be able to make simple calculations of relative intensities at different distances. To begin, let's examine this short video. There is a good chance you already understand the fundamentals of the inverse square. You see this phenomenon happen every night. What is happening as the lights get closer? Do they get more intense or do they get less intense? If you think the lights are getting more intense and your reasoning is due to the light source getting closer, you are well on your way to understanding this concept. Astronomers refer to this phenomenon as the inverse square law. The total amount of light energy that a star produces each second is termed its luminosity, L, and would have units of joules per second. Since stars are far enough away to be point sources, the light is spreading out equally in all directions, distributed over the surface area of a sphere whose radius r is the distance to the star. Since the surface area of a sphere is equal to 4 pi r squared, the intensity I of light that we see or measure with an instrument is given by I equals L divided by 4 pi r squared. Intensity equals luminosity divided by the surface area of a sphere. The SI unit of intensity is joules per meter squared per second. Note that the luminosity of the star is constant, as is the 4 pi, so the intensity scales as 1 over the separation squared. We can explore this phenomenon with the following apparatus. We have a light source, a fiber optics cable that guides the light to a photometer that measures its intensity, an interface to interpret the photometer's readings for a computer application, and a bulb sitting on a cart that reports its position to the computer. We can physically move the light bulb, changing the distance between it and the detector. We dim the lights and turn on our light bulb. We begin with the light bulb about 20 centimeters from the optical fiber. We start measuring the intensity of light and gradually increase the distance between the light bulb and the optical fiber. When we carefully take intensity readings at a range of distances, we get the curve shown here, clearly displaying how light falls off as 1 over distance squared. Let's explore our understanding of the inverse square law with a pure instruction question. Compare the intensities of light through patches on concentric spheres centered on the Sun. Imagine that concentric spheres are placed around the Sun at radii of 1, 2, and 3 units. If the flux through the red path on shell 1 is 4, then the flux through the blue patch on shell 2 is A, 0.25, B, 1, C, 4, or D, 16. Classroom students should follow normal procedures or instructor guidelines. Viewers not in a classroom should record your vote and explain your reasoning on a piece of paper. Please pause this video and answer the question. Note that all of the light energy that passes through the red square also passes through the 4 blue squares. Thus, the light intensity at a blue square must be 1/4 of that through the red square. The inverse square principle is of great importance in astronomy as it is often difficult to obtain the distances to objects. There are several bins of astronomical objects known as standard candles, meaning that all members of each group have similar characteristics and we have a pretty good idea of how luminous they are. Examples include pulsating stars like RR Lyrae stars and exploding stars like Type 1a supernovae. Every Type 1a supernovae has the same luminosity at its peak brightness. Astronomers measure the intensity of these objects, and since they know how luminous they are, they can then calculate their distances using the inverse square law. More teaching materials can be found at astro.unl.edu.